Today's topic is on graph theory, very elementary graph theory. Actually, the number one is not very accurate because last week we already talked about something about graphs. Okay, so let me remind you where we are. Okay, last week we are talking about Euler works, right? And today we'll see some other versions or some variations of Euler's work. And then there is a related application or question. Somehow it's called Chinese postman problem. We'll see what it is. And then the last item is about vortex coloring. And it has also some applications. Okay, so let me remind you what is Euler's work. Okay, so an Euler work is in a graph is a work that uses every edge in the graph exactly once. So an Euler work can be open or closed. By closed, it means you have to return to the point where you started. Right? For open, you don't need. You can start from somewhere and end up with a different place in the graph. Okay. So we stated the theorem 1 and 2, and we give a proof of 1. So let me remind you what did they say. So theorem by Euler says a connected graph has an Euler circuit if and only if the degree of every vertex is even. The degree of a vertex means the number of edges coming out of the degree, coming out of the vertex. Okay, so so the theorem says there is an Euler circuit if and only if the degree of every vertex is even. And the second part says a connected graph has an Euler walk starting at one place, vertex A, and end at vertex B. B is different from A. If and only if A and B have odd degrees and every other vertex has even degree. So this is a criterion of having an Euler open walk. So I give a proof for this, and somehow it attracts some questions. So I want to, okay, I will not repeat the proof, but I want to use an example to tell you the idea of the proof. Okay, so I just tried this annotator. It seems work today. So okay, so let's. So I'll use the example I had last time. Okay, so so let's choose this. Okay, so last time we have seen this graph. Okay, good. So it's something like this. And we have that. Right. Okay, so this is a graph. So these are the vertices. Okay, so here you can make it okay. So we have 8 vertices and couple of edges. So let's label them. Let's label the vertex, right? So let's say this is A, this is B, this is C, this is D, E, F, and G. G is here. Okay? So this is a graph. So we want to know whether there is a Euler circuit or Euler walk here in this graph. Okay? So let me remind you what is Euler circuit or Euler walk. Okay. So you have to travel through every edge, but you travel through it only once and exactly once. You cannot miss any edge, and you cannot repeat. So you have to travel it once and exactly once. Okay. So now, does the Euler theorem apply? So here, let's count the number of degrees of each vortex. So the degree of A is 2, right? Because it has 2 edges connecting to vortex A. So A and D has degree 2. And this B, C, E, F, and G, they have vortex 4, right? Because, for example, B has 1, 2, 3, 4 edges connecting to B, right? The guy in the center, 1, 2, 3, 4, right? So every vertex has degree either 2 or 4. They have even degrees. The degree is even, right? So based on Euler theorem, we should have an Euler circuit. So we can we can trace the graph, right, without lifting our pen and without retrace any particular edge, right? So what? Okay, so let's do it, right? So let's find Euler circuit from this graph, and then the process of finding that that circuit actually is a proof. So the idea is from the proof. Okay, so in this case, we don't care where we want to start. Okay, so please give me just give me a letter, right? Pick your favorite vortex from here. A. Okay, so you want to start from here. Okay, so this is our starting point. So let me change the color of the pen. So we start from here. Okay, where do you want to go? You go up or down? I don't care. Up. Okay, so you go here, and then where? Just direct me. Give me a signal. Go to B. Okay. We don't need to produce the Euler graph. No, you just whatever you want to go, whenever you want to go. G. Okay, so okay, fine. C. Okay, everybody can say something. I don't care. Where do you want to go? Then we'll just look at this graph and just give me okay. So there are 2 ways, right? E or D or B. Tell me. E. Okay, and then. Sorry, F. Okay. Oh, then my life is much simpler. So then what? Then G. Okay. Oh, then there's only one way. E. Okay. Okay. So, okay. So we have A, F, B. Okay, you can see it, right? And then we go to G, then we go to C, we go to E, then we go to F, right? And then we go to G, then we go to E. Okay, so this is so far we have done. Okay, so then we miss some of the edges, right? So let's pick a color. Let's say green. Okay, so the graph has to be connected. Otherwise, there's no way. Suppose it's a 2-piece, and then you cannot cross. So the graph has to be connected. So therefore, there must be an untraveled edge connected to the path we had here, right? To the red one, because it's just one piece. So they are. Oh, this graph is so small. So one of them will connect to somewhere. So we have 1, 2, 3, 4 edges missing, right? So just pick your favorite edge from the 4. Give me an edge. You know what I'm asking, right? So there are 4 A, B, B, C, C, D, and D, E. We haven't traveled, right? So you have to tell me which one do you want to travel next. D, D. Okay, good. So DE, okay, so here you want to travel so you start from E to D, and then D you have no choice. You have to go to here. Now in this case again you have no choice, right? Because this is all other possibilities are taken before. So and then you are here, then you have no choice. You have to go down. Now in this case you can finish the Euler circuit by just adding, right, this D, C, B, and A. So you come back to A. Right. So well you see the idea, right? So you just travel whichever way you want to travel, and then the missing part you can add and extend them. In this case, it is a little bit special because we attach the green at the end. Now, in general, you may not. Here. So in general, things may not happen in the end. So maybe you can add a little bit here, so that you can finish this Euler circuit somewhere in the middle. So so anyway, this is just an example. If you want to see the accurate proof, you have to go back to the notes. So the proof basically says this: if you travel to a point, right? If you enter, you must go out, because you cannot stay. If you stay, this guy will have odd number of degrees, right? So if you only have enter, you do not go out, and then this is a single. This is actual degree. So you have to travel out, and then eventually you have to use all the possible edges, and things work out. Okay. Anyway, so that's the sort of example of Euler work and the proof. Okay. So let's talk about the real thing. So we come back here. So hopefully with that particular picture, we understand this, right? So it has an Euler circuit if and only if a degree of every vertex is U. Okay. And these things are similar. Okay. Now you will see I'll show you an example in a moment. Okay. So this is the example. So let's see this. So this graph, we have A, B, C, D, E, right? And then the degree, so degree of A, C, D, and E are all of, they are all of degree 3. And the degree of B is 4. So based on Euler's theorem, there's no Euler work inside this graph, right? Because the Euler work only exists if you have 2 vertices with odd degrees. But this guy has 4, so there's no chance. Okay? So, but the job is not to find Euler work. It says add the smallest possible number of edges to the graph, so that it contains an order work. Right? So this one doesn't have a order work, but we may sort of add some new edges to the graph, and then after we add the edges, the new graph has an order work, right? So we want to know what is the least number of edges, the smallest possible number of edges we add to the graph so that it has an order work. But I guess this is very simple, right? So now you have 4 vertices with all degrees. So if you add 1 edge, you can kill 2 of them, right? Then the remaining one will have 1. You kill 2 of them. There's only 2 vertices with odd degrees, and then you can do it. Right? You are with me, right? Okay. So here, for example, you can add this. You can add a new edge, this arc from D to E, and then there's only 2 vertices, A and C, with odd degree. So you can go from you can start departure from one of them, say A, and then finish the walk and end up with C. Right? This is the Euler theorem tells us. Well, so here's an example. Right? You may find other walks, but let's follow what he does. So A to D, D to C, C to E, E to A, and A to B, B to D, D to E, E to B, E to C. So for example, this is one. You can travel it in a different order. It doesn't matter. But you have to start from one of these and finish at the other. This is the theorem told us. Okay, so this is an example. Now, last time you also mentioned a theorem, but the proof is just one line. But I'm going to use the theorem later, so I want to remind you the theorem, and also I expand the proof from one line to several lines. Okay, so the theorem last time has no name, but very often people call it a handshake lemma because of the reason. The reason is here. Okay, so last time we mentioned the theorem. The theorem says this: in any graph, the sum of all degrees is equal to twice of the number of edges. Okay, so in a graph, it has vertices, it has edges. You can count the number of edges, right? Now, for each vertex, you can count its degree. So you add all the degrees, and you can count the number of edges. Then they have this relation. The sum of all degrees is equal 2 times the number of edges. Maybe look at example, right? Here. Okay. So how many edges? 1, 2, 3, 4, 5, 6, 7, 8. 8 edges, right? Now, degrees. So we have A, B, C, D. A, C, D, E. Each have 3, right? So it's 12. Now B has 4. So 16, right? We have 8 edges. The total degree is 16. So it fits the handshake lemma, right? It says if you add all the degrees, it's equal to 2 times the number of edges. Okay? So the proof, well, this is very, very long-winded, okay? But it's very easy. So think of vertices as people in a party. That's why it's called handshake. So 2 vertices are connected if the relevant pair of persons shake hands. Okay, so I shake hands with him, then there's an edge between us. Okay, so the degree of a vertex is the number of hands that a person has shaken. Right. So the party, and you shake hands, and okay, the degree of the vertex is the number of hands you have shaken. Now, at the end of the party, ask everyone how many people she shakes hands with. Right? So then the sum is the total sum of the degrees. Right? You ask everybody how many hands have you shaken. You add total of them is like the total number of degrees. Right? So that's the sum of everyone's answer is a number of the left-hand side. Right? So it's the sum of all degrees. Now, on the other hand, each handshake contributes a count of 2 to the left-hand side, right? Because I shake hands with him, and the one handshake counts once in me, right? Counts once in him, right? When we add the total number of handshakes, so it counts as 2. So therefore, the left-hand side actually is 2 times the number of handshakes, right? So, but the number of handshakes is the number of edges. So that's why you have this, right? So it's a very, very simple observation. So that's why it is called handshake lemma. So maybe it is easier to remember instead of a theorem. So it's a handshake lemma. Okay. The fact is very simple. Okay, so now this handshake lemma is useful because it has this corollary. So in a graph G, in graph theory, people very often write a graph as a pair of V and E, where V is the set of vertices and E is the set of edges, because these two are the most important component in the graph. So that's why they single it out, write it like this. Okay, it doesn't matter in this corollary. Okay, so in the graph G, the number of vertices of all degrees is even. Is this easy to see? So you look at the graph, right? My favorite graph is this. Okay. So now these 4 guys has odd degrees, right? They have degree 3. So they A, C, D, E, the degree was odd. Now the handshake lemma tells us those kind of vertices must be of even number, right? Indeed, this is 4, right? Okay, so is this obvious? Well, it is obvious, right? So because the total number of the degrees is even, is 2 times the number of edges, so it's even. So you can't have odd number of odd degrees, right? Otherwise, it's odd. Right? So you must have. So the number of vertices of odd degree must be even. Okay. So then it tells us you can always create an Euler circuit by joining the pair of vertices with odd degrees, because they are even there are even number of them. So you add one edge, kill 2 of them, just keep adding, and you kill them all, right? So you not kill them all. You reduce the number of vertices with even with odd degrees. So you can do this, and we'll see an application in a moment. Okay. So that was the Euler graph in Euler work in a graph, and the graph so far is undirected. There's no directions. The edge, you can travel this way, you can travel that way. Now we want to have a variation of the Euler's theorem. So this time we give a direction for each edge. So the motivation is that, okay, so first we introduce something called directed graphs. In short, it's digraph, right? The di comes from directed, the graph is graph. So the motivation is come from real life, right? If we regard a graph as a network of roads, it is not unusual to encounter one-way streets. Right? So sometimes you can only travel in certain ways. Okay. So in other words, we may include an arrow on each edge to indicate the possible direction of travel. Okay. So such a graph with direction indicated on each edge is called a directed graph, or digraph for short. Okay, we can define a walk in a directed graph. Well, just follow the arrow, and then you cannot reverse. You cannot go to the wrong direction. Okay, example. So consider following. This is a digraph, right? So you have A, B, C, D, but each edge now with an arrow. For example, here from A to B, you can only travel one way. You cannot travel directly from B to A, right? You can, because there's no arrow. You cannot reverse the traffic. You cannot travel against the traffic. Okay. So this is digraph. Now we want to look at some examples of walks, right? For example, from A you can follow the arrow, travel to B, and travel to C, and then travel back to A. So this A, B, C, A is a closed walk in this directed graph, right? Simple enough. Now this A, B, C, A, D, C. So this is an open walk because you start from A, you end up with C. So it's an open walk. Now this is a bad. So A, B, C, D. This is not even a walk, right? Because you are illegal. You cannot travel from C to D like this, right? So D, you can only travel from D to C. You cannot travel back. So this is fairly simple. Okay. Now we have a version of Euler's theorem in the directed graph. So it stated like this, right? So you can try to prove it. Or, yeah. Okay, so this is by Euler. So a connected directed graph contains a closed Euler walk, also called Euler circuit, if and only if for every vertex the number of arrows pointing in is equal to the number of arrows pointing out. People sometimes use in degree and out degree. So the number of edges coming in is the in degree of the vertex. The number of edges coming out is called the out degree of edges. So this theorem says a directed graph has an Euler circuit if and only if at every vertex the in degree equal out degree. The philosophy is the same as what we did for the undirected, because what comes in must comes out, right? So here you can match. So if you come in, then there's always available road for you to go out. So the number of in edges is equal to the number of out edges, right? So this is the theory. Quite easy to understand. Right? Now there's a version for the Euler walk, right? So you can start from A, end up with B. Okay, so let's read it. So a connected directed graph contains an open Euler walk, starting from vertex A and ending at vertex B, if and only if there are three conditions. Okay, so one is for A, the starting point. So for vertex A, the number of arrows pointing out is exactly one more than the number of arrows pointing in, right? Because you depart from A, then you never come back. So you have extra departure edge, right? So this is for A. For B, it's the opposite, because you finish the walk at B. So you enter B, you never come out. So you have one more edge coming into B, right? So for vertex B, the number of arrows pointing in is exactly one more than the number of arrows pointing out. Okay? For the others, it must be balanced, right? For the other vertices, the number of arrows pointing in is equal to the number of arrows pointing out. So it's balanced. If you have one arrow pointing in, you must have one arrow pointing out. Right? So this is the theorem. Okay, so let's look at some examples. Right? Does the following directed graph has a closed Euler walk? It's this A, B, C, D, E. Right? So then we have to check whether it satisfies the condition or not. Right? So Euler's theorem tells us if it has a closed Euler walk, the in degree must equal out degree for every vertex. Is this true? For C, okay, right? In degree, if you have one arrow in, one arrow out. How about A? Two arrow in, two arrow out. Okay. Now how about B? Two arrow in, one arrow out. So no, right? So it doesn't satisfy Euler's theorem. So therefore, there's no closed. So no. Answer is no, because the number of arrows pointing to B, right? So there are exactly two arrows coming in and one arrow coming out. So this is not balanced, right? So it violates by Euler's theorem, this does not have a Euler circuit. Okay, let's look at one more. How about this one? The question is, does the following directed graph has an open Euler walk? Okay, so again, we have to look at the in degrees or out degrees, right? So, so here A is, okay, there are 3 arrows coming out, nothing coming in. Now, this graph has no hope, right? Because the Euler theorem says if there is the open Euler walk, the starting point, okay, only the starting point can have one out more than others, but this guy has 3 more than, so there's no Euler walk. Right? We don't need to check others. As long as one vertex is wrong, then it's wrong. Right, so the answer is no, because, for example, at vertex A, the difference between the number of arrows going out and the number of arrows going in is more than 1. So it doesn't satisfy Euler's criterion. Okay. Right, so it's easy. Okay, so then we are moving on to the next topic. It's called the Chinese postman problem. Now, I'm going to state the problem in general at the next slide. So this slide is just an example. Okay, so it's just an example. So here, so imagine a postman. And nowadays with emails, you seldom see postman anymore, right? So anyway, so imagine that someone is a postman, has to start from A and walk along all 13 streets and return to A. Okay, so salesman, the postman just follow the road and so on and so forth, right? So the numbers on each edge represent the length in meters. So this is 50 meter, 50 meter. Okay, so this is a graph like this is often called weighted graphs because you put a number, put a weight on each of the edges. I think in engineering sometimes it's important, right? So this weight can be cost, can be whatever, can be length, can be other things. Okay, so what is the question? The question is find a trail, find a walk that uses all the edges of the graph with minimum length. Okay, we don't need to travel, we need to travel all the edges, but there's no restriction, we can only travel it once. Right? We don't need to create an Euler circuit. Indeed, in this graph, it's impossible to create an Euler circuit because A is of odd degree, so there's no Euler circuit. So okay. So what is the question? The question is, this postman start from here. He has to cover every street at least once. He can cover more. He can travel several times. Doesn't matter, but he cannot miss any of the streets. Okay, so our job is to find such a trail with minimum length, right? You can wander around. You can travel this 100 times, but then the length was too big, right? So you want to find the minimum possible length. Okay, so you see the problem, right? So there's a graph. There's a weight on the edges. Then you want to find a trail which cover every edge, and somehow it still have minimum length among all the possible such trails. Okay, right? Okay, so here's the question in general. Okay, so here's the question in general. So this is called the Chinese postman theorem, postman problem. So given a connected weighted graph, right? Weighted graph means every edge has a number assigned. or a directed graph G. Find the shortest circuit, that is closed walk with smallest weight, that uses each edge in G at least once. There's no restriction of how many times you use, but at least once. Okay. Now, why it is called a Chinese postman? Because this is first studied by a Chinese mathematician, Guan Meigu. You can find it on the internet in the 1960s. So that's why it has this name. Okay, so you see the problem, right? So now we try to use our knowledge in graph theory somehow solve the problem. Okay, so let's analyze the problem. So the simplest case occurs when every vertex in the graph has even degree, because in this case there's an Euler circuit. The Euler circuit will solve the problem because you have to cover every edge once. Euler circuit does it. And Euler circuit is minimum because it didn't waste anything, because it traveled the edge exactly once, right? So Euler circuit will be the guy, the minimum, right? Because it just fit. Okay. So any Euler circuit will have the minimum total weight, since no edges are retraced or traveled twice, right, in the Euler circuit. So that's why it's minimum. But in general, for instance, in our example I just showed you, there are vertices with odd degrees. For example, in this graph, A and H has degree 3, right? These two has degree 3. Okay. Right? So there can't be any Euler circuits, right? So we need to allow the postman to retrace or repeat certain streets. Right? Otherwise, there's no way. It's impossible. Okay. Okay, so now is the place we mentioned handshake lemma. So by the handshake lemma, there are always even number of odd vertices in the graph. Right? That's why I remind you the handshake lemma. So if there are two odd vertices like A and B, then there is only one way of pairing them together. Right? We want to pair them together. We want to pair the vertices with odd degrees together. Okay, so if there's only one pair, well, that's it. That's the pair. And if there are more than, right? If there are four odd vertices, A, B, C, D, right? Because you must have even number of odd vertices. If it's more than 2, then it has to be 4. So it's A, B, C, D. And then there are many ways of pairing it up. So there are actually 3 ways. Why? Because start from A, you can have 3 choices, A, B, A, C, and A, D. Now after you choose the pair, there's 2 left. They have no choice. They have to pair. So in this case, in the case you have 4 odd vertices, there are 3 ways of pairing them up. And now you see the pattern, right? So if you have 6 vertices, then you have 5 times 3 times 1, many ways of pairing them up. Why? From A, right, you have 5 ways. After A chooses his pair, his companion, there are 4 unpaired left. Then we already know that for 4 vertices, the number of ways is 3 times 1. So 5 times 3 times 1. Now in general, you can find this, but we don't need to know so much. The point of listing this out is it increases really fast. Right? You multiply, and then the possibilities are really fast. So why do we care about possibility? Because we want to find the minimum. So maybe one pairing, okay, is not so good. Then you have to try the other pair. Maybe the other pairing is more efficient, right? So you have because we want to find the minimum. So we have to look at all possible combinations, right? So that's why we have considered these pairings. Okay, so that's the difficulty, right? Now, what is the algorithm? So the algorithm to solve the one algorithm solving the Chinese postman problem has 6 steps. I'm going to tell you. So step 1, list all the odd vertices. Okay, we are going to see the example. So it doesn't matter you cannot follow this for 2 minutes. Okay, so step 2 is list all possible pairings of odd vertices. Okay, so that's a lot. The step 2 is a lot. Okay. Now for each pairing, find passes that connect the vertices with the minimum weight. So for each pair, you have lots of possible passes, right? So you have to find the minimum one, the one of minimum weight, right? Okay. Now find the pairings such that the sum of weight is minimized. Okay. So step 4, on the original graph, duplicate the edges that has been found in step 3. So step 3, for each pair, you choose a path which is of minimum weight, right? And then you are going to sort of duplicate the edges that you identified at step 3. Now I have to explain what is duplicate. Okay, so the reason is, in this postman problem, we cannot build new road. The postman cannot just build a new road. So he has to follow the existing streets. So he cannot add new edges. Unlike the example a few minutes ago I showed you, you can create a new edge whenever you want to create. In this Chinese postman problem, you have to duplicate, you have to follow the streets. So you can only repeat the streets, right? So you cannot build a new road. You can only retrace the edges, right? So this is the meaning of the word duplicate. I'm going to show you on picture, then it becomes obvious. Okay. So step 5, the length of the optimal Chinese postman road is the sum of all these edges added to the total found in step 4, right? So here you add some new, you duplicate some edges, there's a number. Then the rest is you have to travel. You have to cover every single street. So you just add the total, right? So that's step 5. Now step 6, a road corresponding to this minimum weight is an Euler circuit in the graph obtained in step 5, right? We know that the Euler circuit supposedly is the most efficient. So that's the algorithm, okay? Now let's apply this algorithm to the example. Hopefully it explains. Okay, here, this is our favorite graph. So we have 2 bad guys, A and H. These 2 guys are of odd degrees, right? So step 1, identify the odd vertices. In our case, they are A and H, okay? Step 2, well, because this is simple, right? So there's only one way. So you can only pair A and H, okay? So we pair them. Now we want to analyze the shortest way of joining A to H, right? Okay, so from A to H, you have lots of ways, right? You can go around, okay, but the shortest way is this graph is small, so it's very easy to see. The shortest way is 50, 50, 60, right? So 160. If you go here, you have 260, 150 is worse. Now here you have 270s is worse, and here you have 70s. So this is the best way. A to B, B to F, F to H, right? So A to B, B to F, F to H. So this is the minimum path from A to H, okay? So the shortest way of joining A to H is using the path AB, BF, and FH. The total length is 160, okay? Now step 4, we draw these edges onto the original network. So this is what I mean by duplicate the edges, right? So you are going to retrace the edge AB. So it's just like you add this dotted line, duplicate the edge AB, right? So the same weight, because you travel forward, backwards, is each time is 50 meters, okay? So similarly for these things. Okay, so this is step 4. Now step 5, you calculate the length. So the length of the optimal Chinese Postman road is the weight in the original network. So that is the total numbers you add up, because you have to travel them. This is a requirement, right? You have to go through every street. So you have to add the total number up together with these 3 new numbers, right? So the length of the optimal Chinese Postman road is the weight in the original work. So you add all the original numbers up together with the answer in step 3 above. That is 160, right? So you add the total number in the total weight in the graph, which is hopefully 840, and plus this, so its total is 1,000. Now, one possible road corresponding to this length, it will be a Euler circuit from the graph with duplicated edges, right? So somehow it says this. You can try. You can just draw it, right? So, but the answer is not unique. You can travel first here, then there, and so on and so forth. Right? So the answer is not unique. But this is a example of the Chinese postman problem. Okay. Oh, okay. So this is a natural place to stop. Well, so let's take a break, and after the break, let's take 5 minutes break. After the break, we talk about vortex coloring. Okay, it's a new topic. Okay, so break. Okay, I guess everybody has returned, right? So let me continue, and probably we'll finish a little bit early. I guess the graph theory topic, the graph take too much space, right? So the number of slides are okay, but the actual content probably is less because lots of graphs. Okay. Anyway, so let's continue. So the third topic of today is about this vortex coloring. So first, let me tell you what does it mean. Okay, so a proper vortex coloring is of a graph is an assignment of a color. Usually we represent it by a number to each vertex of the graph in such a way that any 2 vertices that are adjacent have different colors. So what does it say? So a vortex color is you just give a color to each vertex, right? I like to give this guy red, this guy blue. Okay, our coloring will be numbers. Okay, I'll give this guy color 1, the other guy color 2, and then that's the other vertex color 3, or color 1, color 2 again. So you just assign a color to each vertex. So this is a vortex color. Now what is proper? So there's a rule. The rule says, suppose 2 vertices are adjacent, is connected by an edge, then you cannot color them using the same color. Right? So that's the rule. So that's the proper means. The proper means if you have an edge, then the 2 ends of the edge you cannot color with the same color. Okay? So example. Okay, so you have this funny graph. Now you say, here's a number 1 here. It means I color this vertex with number 1, with color 1. Okay? So then he has 4 adjacent vertices, right? This guy, this guy, this guy, this guy. Now I color them 3, 4, 3, 4. So these, as far as this vertex is concerned, is proper, because at the end of the edge, the colorings are different. This is 1, this is color 3, right? So this is proper. Now let's check some others, right? For example, here, this guy, I color it with color 2. And then he has 3 neighbors. The neighbors are colored 1, 3, and 4. Okay, so it's fine, right? So you can check others. This is an example of a proper vertex color. Now how about so it says there are 4 different colors used in the above coloring, right? It's 1, 2, 3, 4. Okay. Now let's look at illegal, not proper coloring. For example, suppose I color it this way. Now, look at this edge. At both ends, I color the edge with color 2. That's illegal. That's bad. That's not proper. Okay, so we cannot do this, right? So this is, the following is not proper vertex coloring, because this edge you have on both ends you have the same color, right? So this is bad. Okay, so now what? Now we are interested in a proper vertex coloring of a given graph G using the smallest possible number of colors, right? So this has some application we are going to see at the end of the lesson. Okay. So we are interested in vertex coloring with a minimum number of colors. Okay. So such a coloring is called minimum proper vertex coloring. Right? It's not very surprising. It's minimum proper vertex coloring of G. The number of colors that occurs in the minimum proper vertex coloring is called chromatic number of G, and denoted by this Greek letter chi G, chi of G. So it's a chromatic. Chromatic is fancy way of saying color, right? So it's a. Okay, examples. So find a minimum proper vertex coloring of the following graph. This graph is just 3. It's a triangle. So what is the chromatic number of this graph? Okay, right. So let's try, right? So I have to color this guy, say 1. Okay. Now then these two cannot color by 1. I have to choose, at least have 2 colors, right? So if I color this guy 1, and then these 2, so I must color one of them, say, with a different color, say 2. Now if I color this guy 2, I cannot color the bottom one also with 2, because he is connected to this one, right? So I have to use a 3rd color. So this is 3. I need a 3 color to color this simple. Okay. Now the triangle is a special case of something called a complete graph. So definition. The complete graph on n vertices is a graph on n vertices such that any 2 vertices are joined by an edge. And this is called K. K probably is the German version for C, right? It's complete. K sub n. Okay. Now this is K sub 3, because you have 3 vertices and they're all connected. No matter which 2 vertices you choose, they are connected. Okay. So now, question for you: what is a chromatic number for K4? So what is K4? Hopefully it still works. Good. So I have 4 vertices. Now, the definition for complete graph says any 2 vertices are joined. Okay. So I have to join these, I have to join these, I have to join this, 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 right? So I have 4 I have 4 vertices. 1, 2, 3, 4. But I have to join any pair of vertices. So this is K4. Okay. Okay, so to color K4, what is a proper? Okay. What is a chromatic number? 4, right? So, okay, let's do it slowly. I try to save, right? So I color this guy with number 1. So I color this one number 1. And then I have to color him with a different color because they are connected, right? This is 2. Now this guy is connected with both 1 and 2. So he has to use a different color. So he has to use 3 at least, right? Now the last one, again, because it's complete, so he is connected to all the 3 vertices. So he cannot use 1, he cannot use 2, he cannot use 3, so he has to use 4. So that's why you get 4, right? So you see the pattern, right? Now what is a chromatic number of K5? Should we draw a K5? Okay. I have 5 vertices, so I have to connect every one of them, right? So this is K5. Sorry. Right, so you connect all of them. So now, no prize for guessing what is a chromatic number, 5, right? So you have to use 5 because similar reasons. Okay, so what is a chromatic number for K sub n? N, right? So the same reason. Okay, so now here's some application of the observation. So people call it a vertex coloring theorem. Okay, so the theorem says if a graph G contains a complete graph on n vertices, suppose it has a K4 or K5, then a proper vertex color of G, coloring of G, must use at least n colors. In other words, the chromatic number of G is at least n. It's bigger than or equal to n. In other words, if you contain K4, you need at least 4 colors. Right? If you contain K5, you need at least 5 colors. This is obvious, right? Okay, so for example, find the minimum proper vertex coloring for this G and determine its chromatic number. You can try, right? So okay, so the answer is okay. So you can try. So the answer is you can do something like this, so that you only need 3 colors. Okay. So for example, if you color it like this is a proper coloring using 3 colors. So the chromatic number is at most 3, right? So you are able to color it with 3 colors. It means the minimum possible color is definitely less than or equal to 3. Okay. So chi of G is less than or equal to 3. Now how do you know you need at least 3? Well, there is a triangle. This graph contains a K3, right? A complete 3 graph. So the graph contains a complete graph K3. In other words, it contains a triangle. And we have seen that just for that triangle, you need 3 colors. So there's no way to save, right? So by the vertex coloring theorem, the chromatic number is at least 3. So therefore, it is exactly 3. Right? So the reason is quite simple. Now, another example. Find the minimum proper vertex coloring for this graph G below and determine its chromatic number. Should we try? Okay, so let's try. So we have to start from somewhere, right? So we just try. Right? So this is 1. And then, I don't know. So we try 2 here. Now there's a triangle, so I have to use 3. Right? Now how about this one? This one I can use 2 again. Right? Because I have to use something different from 1, different from 3, so I use 2. Okay? How about this? I can use 3 again. Right? How about this? I can use this guy connect to 1, connected to 3, also connected to 2. So I have to use 4. Right? And then this I can use 1. Okay? So this is one of the colors. Right? Whether this is minimum, I'll leave it to you. Okay. So try to see whether you can save some. Okay, so I think the minimum is 4, but I'll leave the argument for you. Okay, let's look at some more examples. Okay, so for example here, find a graph whose chromatic number is 3, but it does not have a triangle. Okay, well, this is transparent, so you can see it. So the solution is you can have a pentagon like this, right? So the pentagon will have chromatic number 3. Why? Let's try. So I start from 1. So I try my best, right? So I do 2 here. And this guy, again, I want to save, so I use 1, right? Because that one is not connected. And then here I can recycle 2. Because this is a pentagon. So here I'm going to meet a vertex which is connected both 1 and 2. No choice. I have to use 3. Right? So therefore for this graph, the chromatic number will be 3. But it doesn't have a triangle. Right? It's a pentagon. Okay. Now the same logic applies. This is a 7, I think 1, 2, 3, 4, 5, 6, 7. So if you have 7 edges, you have the same logic. Right? You color this guy 1, then 2, 1, 2, 1. Here you have no choice. Right? 2, 1, 2, 1, 2. And then the last one you have to use 3. So that give us some hint. Right? So in general, we can conclude something like this. Okay, so first let's give this kind of graph a name. So this is called the cycle graph. Right? So definition of cycle graph of length n is denoted by C sub n. So the cycle graph is just like this. Okay. So for example, the example here, this is C7 because it's a cycle with length 7. Okay. Last time we have defined cycles inside the graph, right? Now, if a graph itself is just a cycle, then we call it a cycle graph. So it's very easy to understand. Okay, so now what is the chromatic number of the cycle graph Cn when n is odd? We have seen C3, C5, C7, right? So we all use 3 colors. So if n is odd, we can use 3 colors to color them, right? How about the n is even? Do we still need 3 colors? Okay, so let's look at a hexagon like this, right? I color this at 1, 2, 1, 2, 1. Oh, I'm lucky. Here I can put 2. So if it's even, certainly you can use 2 colors, right? So you cannot use 1, obviously. So this is the chromatic number for this is 2. Okay, so now so here's another vortex color theorem, right, which tell us the lower bound of the vortex, the chromatic number. Right? Just now it says if it has a complete graph, Kn, and then it is at least n. Right? Here it says if it contains a cycle graph, Cn, right, and n is odd, then the chromatic number is at least 3. Right? Because we just observed, just to color that cycle, you need 3 colors. So you cannot get any less. So you need at least 3 colors. Okay, so for example here. So find the minimum proper vortex coloring for this graph and determine its chromatic number. Okay, so first you can color it using 3 colors. So it's 1, 2, 1, 2, 3, and somehow here you use 2, and then you do this once, okay, 2, 3, 2, 3, 1 is here, so it's okay. So you can use this. So you can use 3 color to give a proper coloring. Now the theorem says you cannot get less because in this graph you have a 5 cycle. And then to color the 5 cycle, you need at least 3 colors. So you cannot get less. So the chromatic number is 3. It's all quite easy to see. Okay. Now this one is slightly more complicated. Just now we see the lower, we call it lower bound. We saw the chromatic number is at least 3, right? At least n. So now we want to give an upper bound. We want to say that it at most something. So here's the algorithm. Okay, so there's a algorithm to give an upper bound. You'll see that this upper bound is not optimal, but nevertheless it gives us an upper bound. Okay, let's see the algorithm. Okay, well, this is a general algorithm. In a moment we'll see examples. The example will make things easier. Okay, so the theorem says this. Okay, first arrange the degree of the graph in decreasing order. Okay, so it's D1, D2, D3. I'll use the example in a moment to tell you. Okay, then you place integers 1, 2, 3 directly under these degrees until you reach an integer k such that k plus 1, so here, so 1 below D1, 2 below D2, 3 below D3, k below dk. The next one, k plus 1 here, somehow this k plus 1 is bigger, strictly bigger than dk plus 1, bigger than this number on top. In this case, we know that for this graph G, the upper bound is the chromatic number of G is at most k plus 1. Okay, try again. You arrange the degree of graph in decreasing order, and then you write numbers like 1, 2, 3 until the moment that you get a bigger number. You get the number on the second row bigger than the number on the first row. Okay. In that case, this number k plus 1, the first number you stop is the upper bound of the chromatic number. Okay, to abstract, look at this. So I want to use this algorithm to get an upper bound of the chromatic number of this. Okay, so now we need to first list the degrees in decreasing order. Okay, so let's check. The degree 3, degree 4, degree 3, degree 5, 3, 3, 4, 5, 3, 3. Okay. So you write the degree sequence in decreasing order. So we have 2, 5, 2, 4, and all others 3. Is it true? 2, 5, this guy is 5, this guy is 5, 2, 5. 2, 4, this guy is 4, this guy is 4, all others are 3. Okay? So we have this. So that's the degree, the sequence of degree in decreasing order. Okay? And then we are going to write 1, 2, 3, 4, right, from this side. So 1, 2, 3, 4. Wait, the next one. I'm going to write 5, but 5 is strictly bigger than the guy on top, right? So I stop. Okay, so the number I'm going to write is an upper bound. So the conclusion is the chromatic number of this graph is less or equal to the number I'm going to write down, the 5. So 5 is enough. You see the algorithm? Okay. Probably I have another, I don't know, maybe I have another example, but okay, so let's see why it works. Okay. So here's the reason why it works, right? It's something I could prove. If every vertex in the graph has a degree at most k, then we need at most k plus 1 colors in the minimum proper coloring. Because you can always find a different, right? You can give them different colors. Right? Now the upper bound algorithm instructs us to color the vertices one by one in decreasing order of the degrees, using a new color at each step. Okay, it's not optimal. We'll see an example. So what does it say? So it says we should color there are 2 degree 5 vertices. You color one with 1, the other one is 2. There are 2 degree 4, so we color one with 3 with 4. Now then the rest, we are able to handle them very easily because the degree, each one of them is not connect more than 3 of them. So you can handle them. Okay, so let's come back here. So the upper bound algorithm instructs us to color the vertices one by one in decreasing order of their degrees, using a new color at each step. When the algorithm stops, in other words, when the moment the number on the second row is strictly bigger than the number of first row, we already used k colors, right? And all the remaining vertices now have degree at most k, because k plus 1 is bigger than this dk plus 1. So the dk plus 1 is at most k. So by the reasoning here, if a graph has degree at most k, then if every vertex of the graph have degree at most k plus 1 color will do. Right? So the k plus 1 color is sufficient to handle the rest of the graph. Right? So now by 1 we know that no new color are ever needed to color the remaining vertices. So we are done. So that's the reason. Okay. So here we have another chance to. Okay, we don't care too much because this is a general education module. We don't care too much about proof, but we have to know how to apply. Right? Okay, so now we have this funny graph. We want to practice this upper bound algorithm. So what should we do? You look at the degrees, right? So, okay, so let's from top work on to the bottom. So this is degree 3, 3, 3, 4, right? This is 4, right? This is 4. This guy, 5. This guy, 4. 1, 2, 3, 4. This guy, 3. This guy, 4. This guy, 3. Okay, so the big one is 5, right? And then there are several 4, right? This is 4, this is 4, this is 4. And then others are 3. Is it right? Okay, so the degree sequence in the decreasing order is this. Okay, one vertex with color, with degree 5. Okay, degree 5. And then 4 vertices with degree 4. The remaining guys are degree 3. Okay, so we have this sequence. Now, we apply this upper bound algorithm. So we write 1, 2, 3, 4 here. Now this guy, 5, I'm going to write 5. 5 is strictly bigger than 3, right? So I stop, and then this, the number I'm going to write is the upper bound of the chromatic number. So the chromatic number of G is less or equal to 5, at most 5. Okay. Now indeed, so we said a few times this may not be optimal. Indeed, this funny graph, you can color it in 3 colors. So, for example, here's a way of coloring it in 3 colors. I think this is legal, right? You can check. So actually, the chromatic number is less than or equal to 3 because I can color it using 3 colors. Can I get less? No. The reason is we have triangles, right? For example, here. If you have a triangle or you have an odd cycle, whatever, then you cannot have 2 colors. So at least 3. So therefore, the chromatic number of this graph is 3. But the upper bound algorithm tells us it's at most 5. It's correct, right? If it's 3, it's less than 5. But it's not the optimal, right? Yes, you can color it using 3 colors. You don't need 5. Okay, so I hope the algorithm is simple enough to follow. Okay. So now there are some, why do we care? There are some applications in real life, right? Living with math in our real life. So today I give you one example. So it helps us to do something called scheduling or store things in places. So this is an example of about storage. Okay, so here, so there is a call it chemical factory. A particular chemical factory produces 13 different kinds of chemicals. So labeled by C1, C2, C13. Okay. So the following table shows us, next slide shows us, it is not safe to store the chemicals in the first column with those on the second column. Okay. In the same okay. So you cannot put them together. Okay. Otherwise, if it's not on the list, then it's okay. You can store them under the same roof. Okay. Right. You can store them together in the same warehouse. Okay, the question is, what is the minimum number of warehouses that the factory needs in order to store the chemicals safely? Okay, so the restrictions are like this. So, for example, C1, you cannot store C1 in the same room with C2, C7, C6, C12, or whatever. So you cannot store C2 with C1, C3, C7, C8. And so on and so forth, right? You cannot store C10 with C4, C5, and C13, right? So there are restrictions in this table. So the chemicals have their enemies. You cannot put them together. Okay. So is the question clear? So we have 13 chemicals. We want to store them safely. Now we know that there's restrictions. The restrictions is given us in that table. Okay, so the question is, what is the minimum number of warehouses that the factory needs to build? Of course, if you build 13, fine, right? You store a single chemical in one warehouse is fine, but that's obviously not what we want. Okay, so we want to use the vortex coloring to help us. So the solution for this is we construct a graph as follows. So the vortices are the chemicals, the C1, C2, C13. Okay. So now the edges, so we join Ci and Cj if they appear in the same row. Okay. If you cannot store Ci together with Cj, you connect them. Right? As you know, because we want to use colorings. So if you connect them, you cannot use same color. So that's why you do this. Okay, so let colors represent the warehouses. Then we must put different colors to adjacent vertices, right? Because you connect them because they are dangerous to put together. Okay, so the minimum number of warehouses needed is just a chromatic number of that graph, right? So it has some application. Okay, so I don't know how accurate this is. Many of you are very sharp, so this is the graph created based on the list. Okay, something like this. So you have 13 chemicals, and you connect some of them because you cannot store them in the same warehouse. Okay, so this graph contains a triangle. So at least you need 3 colors. Right? Now, can you find a coloring use exactly 3 colors? Okay, so according to the notes, you can. Is it true? Right? It's legal. Right? Everything was legal. Okay, so you can have a 3 coloring of this, and then this is the best. So the chromatic number of this graph is 3. So you actually need 3 warehouses, and then you just put, say, the guy colored it is the same color. Put them together because they are safe, right? They have no connection, so it's not dangerous to store them together. Right, so the minimum number is 3, right? Okay, so that's all for today. So next, on Friday, I think there are some interesting topics in the graph theory, but for example, 4-color theorem, or so there are something interesting. So I'll probably, okay, I need to cover trees. And also, there are some fun facts about graphs. So I'll use probably 1 hour to talk about graphs, and then we move on to the next topic, which is probably about coding or something. So see you on Friday. Today we finished a little bit earlier.